Linux Kernel 7.0 is finally here, and it brings some really exciting improvements that every Linux user should know about in detail. Whether you're running Ubuntu, Fedora, Arch, Linux, Debian, OpenSUS, or any other distribution out there, this new kernel version is going to make a noticeable positive difference in your daily computing experience. Released officially on April 12, 2026 by Linus Torvalds, version 7.0 marks a significant milestone as it ends the long-running 6.x series and opens up a fresh new chapter in kernel development. Many in the community get particularly excited when they see a major version number jump like this from 6 to 7 because it feels like a big step forward. But as Linus Torvalds has reminded everyone many times in the past, these version bumps are not usually complete revolutions that rewrite everything from scratch. Instead, Linux Kernel 7.0 represents a very solid and thoughtful evolution packed with important bug fixes, meaningful performance gains, better hardware support, and new capabilities that developers have been working on steadily over many months. In this video script, I am going to walk you through 7 of the biggest and most impactful changes in Linux Kernel 7.0 that you absolutely need to know about if you care about your system's performance, stability, and future compatibility. We will explore each change in depth, discussing exactly what they mean for everyday desktop users, laptop owners, server administrators, gamers, developers, and even those thinking about future hardware upgrades. By the time you finish watching or reading this, you will have a clear understanding of why this kernel matters, how it directly solves some long-standing problems that Linux users have been complaining about for years, and whether you should consider upgrading your own system right away. To give you some important context before diving into the details, let us first talk about why we have version 7.0 right now. The previous 6.x series had gone all the way up to 6.19, which was quite a long run. Linus Torvalds had publicly mentioned in mailing lists and interviews that he was essentially running out of easy ways to keep counting the minor versions comfortably without it feeling awkward, so rather than pushing out a 6.20, the decision was made to jump straight to 7.0. This kind of versioning change is not connected to any massive architectural overhaul like what you might see in commercial operating systems from big companies. However, it does provide distribution, maintainers, hardware vendors, and open-source developers with a clean slate for better tracking of changes moving forward. Major distributions have already started adopting it quickly. For example, Ubuntu 26.04 LTS ships with Linux Kernel 7.0 as the default option for new installations and upgrades. Fedora 44 also includes it out of the box, and users on rolling release distributions such as Arch Linux, OpenSUS, Tumbleweed, Gen 2, or Cashios are already receiving it through their regular update channels. If you are still running an older kernel from the 6X series on your machine, making the switch to 7.0 is likely going to feel refreshing and worthwhile once you understand the benefits. With that background in mind, let us now dive straight into the first major change that has the entire Linux community talking. The very first and perhaps one of the most talked about improvements in Linux Kernel 7.0 is the promotion of Rust, language support from an experimental status to a fully stable and production-ready feature inside the kernel. For several years now, Rust has been gradually making its way into the Linux kernel as a modern and safer alternative to traditional C code for writing device drivers, modules, and other critical components. In earlier kernel versions, Rust support carried an experimental label, which meant developers were encouraged to use it cautiously, and it was not yet considered fully reliable for mainstream use. But with the arrival of Kernel 7.0, that experimental tag has been completely removed, marking a major turning point. This is genuinely huge news for the long-term health of the Linux ecosystem because Rust introduces strong memory safety guarantees at the language level. These guarantees help prevent entire categories of serious bugs, such as buffer overflows, use-after-free errors, null pointer dereferences, and other memory-related vulnerabilities that have unfortunately plagued C-based code for decades, despite careful programming practices. What does this Rust stabilization actually mean for you as an ordinary everyday Linux user who may not write kernel code? It translates into more reliable and robust hardware drivers becoming available over the coming months and years. Developers can now confidently write new drivers and subsystems in Rust without worrying as much about introducing dangerous low-level mistakes. We are already beginning to see early contributions that benefit real hardware, including improved support for Apple Silicon platforms and certain AMD GPU components that are getting the Rust treatment for better maintainability. It is important to emphasize that this does not mean the entire Linux kernel is being rewritten in Rust all at once. The vast majority of the codebase remains in C, which is still the primary language. But the fact that Rust is now a first-class citizen alongside C sends a powerful signal about the direction of future development. Over the long term, this shift should result in fewer random kernel panics, stronger overall security posture, and faster development cycles when bringing support for brand new hardware to Linux. If you have ever dealt with a flaky Wi-Fi adapter that drops connections randomly, a graphics driver that crashes during intense gaming sessions, or storage issues that appear out of nowhere, then the gradual benefits coming from stable Rust integration are going to help address those frustrating problems more effectively than before. The kernel maintainers organized a dedicated summit toward the end of 2025, where they carefully evaluated Rust's readiness, ran extensive testing, and ultimately declared it ready for prime time. Kernel 7.0 is the release that fully delivers on that promise. This single change by itself makes version 7.0 feel like a genuinely future-proof update that positions Linux well for the next decade of computing. Moving forward to the second significant improvement, Linux kernel 7.0 brings much better memory management overall, with particularly impressive enhancements to swap performance that will help many users. Swap space has traditionally been one of the weaker areas in Linux for people running systems with limited physical RAM, such as budget laptops, older desktop machines, or virtualized environments. When your RAM fills up and the system has to start swapping data to disk, things could quickly become painfully slow and unresponsive in previous kernel versions. In 7.0, the swap subsystem has undergone further optimizations that build directly upon the foundation laid in the later 6.x releases. The result is noticeably better throughput, even when the system is under heavy memory pressure. Your computer can now handle situations where it runs out of available RAM in a much more graceful manner, avoiding extreme freezing or excessive disk thrashing that used to make the machine feel almost unusable. This kind of improvement is especially welcome in today's environment, where RAM prices remain relatively high and a large number of users are still operating with only 8 GB or 16 GB of memory. The technical gains come from smarter page reclamation algorithms, improved integration with fast, modern solid-state drives, and more intelligent decisions about what data to move in and out of swap. If you frequently use features like system hibernation, edit large video projects, compile big software projects from source, or run several virtual machines at the same time, you are going to appreciate how much smoother these workloads feel now. The kernel has become better at reclaiming memory pages efficiently and only swapping out the absolute minimum necessary information. This directly solves a very common user complaint, where older kernels would cause the entire desktop to slow to a crawl, even when swap usage looked moderate on paper. When these memory management tweaks are combined with other related optimizations throughout the kernel, Linux 7.0 generally feels a lot snappier and more responsive during multitasking sessions. For those running servers with containerized applications or database workloads, the benefits show up as higher container density and improved resource utilization, meaning you can often get more work done on the same hardware without needing expensive upgrades. Overall, these memory changes make Linux feel more capable on modest hardware configurations. The third major area of improvement in kernel 7.0 centers around the process scheduler, and this update is going to deliver a noticeably smoother experience, especially for desktop and laptop users. The new kernel enables lazy preemption by default and introduces an innovative RSEC-based time slice extension mechanism that helps threads complete critical work more reliably. To explain this in simpler terms that everyone can understand, previous kernels sometimes interrupted running threads too aggressively in the middle of important operations. This could create small but annoying microstutters during gaming, video playback, web browsing with many tabs open, or even just smooth scrolling in applications. With the new restartable sequences approach in 7.0, active threads now get a bit more predictable breathing room to finish sensitive code sections before the scheduler decides to switch them out. This leads to reduced overall latency and a system that feels much more responsive when you are pushing it hard. Lazy preemption adds another layer of intelligence by postponing unnecessary context switches whenever possible. These scheduler enhancements prove particularly valuable on modern hybrid CPU designs, such as Intel's Big Little architectures or AMD's processors that mix different core performance levels. Linux gamers are reporting fewer spikes in frame times. Regular desktop users enjoy better multitasking fluidity, and laptop owners may even see modest improvements in battery life because the CPU does not waste as much energy on frantic switching. Adaptive scheduling domains now adjust dynamically to balance workloads across available cores more efficiently than ever. If you have ever felt that the Linux desktop experience, while good still, fell slightly short of competitors in terms of consistent smoothness during demanding workloads, then this scheduler work in Kernel 7.0 directly tackles that remaining gap. It is the kind of deep under-the-hood improvement that rarely makes big headlines but delivers real daily satisfaction once you start using it. The fourth notable feature is the introduction of a new generic file input-output error reporting API. This has been something the community requested for a very long time. In the past, different file systems handled and reported errors such as metadata corruption or unexpected I/O failures in inconsistent ways, making it difficult for applications and monitoring tools to react appropriately. Kernel 7.0 standardizes this through an improved FSNFI-based mechanism so that user space programs receive clear, consistent, and actionable error notifications. System administrators and anyone who values data integrity will find this extremely useful because monitoring tools can now listen for these standardized events and warn you proactively before minor issues escalate into serious data loss situations. The change is especially powerful in large storage arrays, enterprise servers, or any setup where continuous uptime and reliability are non-negotiable. When paired with other file system advancements, it helps Linux feel more mature and enterprise-grade, even on regular desktop machines. It enables better background disk health checking integrated into graphical tools so you do not always have to drop to the terminal and run manual diagnostic commands. This update effectively resolves years of fragmented error handling practices across the many file systems Linux supports and brings everything together under one cleaner and more reliable system. Continuing with storage-related improvements, the fifth big change involves enhanced capabilities in the XFS file system for autonomous self-healing and real-time health monitoring. XFS has long been a favorite high-performance file system for handling large amounts of data, and Kernel 7.0 pushes its abilities even further. It can now automatically detect and repair certain types of metadata corruption, while the file system remains mounted and in active use, without forcing you to take it offline for repairs. Live health status information is exposed to user space so you or your monitoring scripts can keep an eye on file system integrity continuously. This represents a major step forward for database servers, media libraries, backup systems, or any large file sharing setups. Other file systems also benefit. BTRFs receives experimental remap tree functionality, along with improved direct I/O performance in cases where block and page sizes do not match. A new immutable root file system option called NULFs appears for specialized container or secure boot scenarios. NTFS3 driver performance sees nice gains which will please dual boot users who regularly access Windows partitions from Linux. Taken together, these file system updates mean you will run into fewer forced FSCK checks after unexpected shutdowns, enjoy faster recovery when problems do occur, and experience more dependable long-term storage behavior. Anyone who has wasted hours waiting for file system repairs after a crash or power outage will particularly appreciate how Kernel 7.0 reduces that kind of downtime and frustration. The sixth key area of progress comes in networking. Accurate, explicit congestion notification, often abbreviated as a Keysian, is now turned on by default. This leads to smarter TCP congestion control and more efficient bandwidth usage across varied network conditions. IPv6 handling receives optimizations in the TCP output path with improved flow catching. UDP performance is boosted for demanding high-speed applications, and there is tighter integration with popular COS schedulers like Cake that many home users rely on for better router performance. These networking upgrades benefit a wide range of people, from casual users streaming high-resolution video content all the way up to professionals managing high-throughput servers or data centers. You should notice lower latency during congested periods and higher overall throughput on your connections. Gamers and remote workers juggling multiple devices will likely enjoy more stable and predictable network behavior. The kernel developers have invested serious effort into making the networking stack keep pace with today's fast internet demands, while also laying groundwork for upcoming protocols and even higher speeds. If you have experienced buffer bloat issues or felt that Linux networking sometimes lagged behind other operating systems in real-world consistency, these 7.0 updates go a long way toward closing that remaining performance difference. Finally, the seventh major category covers expanded hardware support together with sensible cleanup of outdated legacy code. Kernel 7.0 adds native atomic 64-byte operations for ARM64 platforms, introduces new security-focused extensions for RISC-V architectures, and brings 128-bit atomic support to LungArch systems. There is also forward-looking preparation for the next generations of processors from AMD and Intel, including Zen 6 and Nova Lake families. On a lighter note, quirky additions like support for Rock Band for Bluetooth drum controllers made it in for enthusiasts. At the same time, truly ancient hardware support, such as i486, compatibility is being phased out to help keep the kernel codebase leaner and more focused on modern platforms. Graphics drivers include important stability fixes for Intel Xe2 and various AMD configurations. This broad hardware enablement strategy ensures that brand new devices receive working support sooner after launch. While the kernel avoids carrying unnecessary weight from decades-old technology, security receives ongoing attention too, with preparations for post-quantum cryptography, algorithms, and improved processes for reviewing code contributions that might come from a BIOS-assisted development. Beyond these 7 headline features, Linux kernel 7.0 contains hundreds of smaller but still valuable fixes, driver updates, and subtle performance enhancements scattered throughout the codebase. The IO_Uring asynchronous I/O framework is more capable with expanded filter support. Setting up containers feels faster thanks to new open_tree flags, and static analysis tools using Clang have been improved to catch potential bugs earlier in the development cycle. When you put everything together, Kernel 7.0 comes across as a polished, mature, and very usable release that is ready for daily driving on almost any system. If you are wondering about the practical steps for installing this kernel, the process varies depending on your distribution. Ubuntu 26.04 users already have it by default. Older Ubuntu releases might receive it later as a backport. On Arch or other rolling releases, a simple system update command is usually enough, no matter what. Always create a good backup of important files before performing a kernel upgrade, and consider tools like Timeshift or Snapper that let you roll back easily if something unexpected happens. Testing the new kernel inside a virtual machine first is a smart precaution for cautious users. The majority of people upgrading will notice immediate gains in responsiveness and general reliability. Although it is wise to keep an eye out for any rare hardware-specific issues and report them to the kernel developers if they surface,